Hey guys, hope everybody's doing okay. What we're going to do today is look at something called determination of percent yield, and this is actually the last lesson in our stoichiometry unit. So when we talk about percent yield, we want to talk about an actual chemical reaction. Hey guys, hope everybody's doing okay. What we're going to do today is look at our last lesson in our stoichiometry unit, which is called determination of percent yield. When we think about percent yield, we want to think about a chemical reaction, and we want to think about a lab experiment or a lab experience that we are doing. So what we've done so far throughout the unit with our basic stoichiometry problems and our limiting reagent problems is, for a lot of them, we've been figuring out how much product we should actually make. Okay, a theoretical amount of product that if we did the chemical reaction or experiment and everything went perfectly fine, we should make X amount of product. Okay, so the math tells us, the stoichiometry tells us how much we should make. All right, now we know from reality, from doing a couple labs throughout the year, that you don't always make how much you actually should. Okay, so the same thing could be applied to some real life situations like maybe making brownies or making cookies. So you follow the recipe exactly as it says. And maybe the recipe says mix together, all the ingredients and you should make 24 like 2-inch wide cookies. You're like, okay, fine, I mix together everything, I follow the directions just like I should, and I make the cookies the exact size they tell me to make them, and I only make 22 cookies, and I should have made 24 cookies. You're like, well, what gives here? How am I 2 cookies short? I follow the directions just like I should. Well, you have to think of that process that you follow to make those cookies. You are mixing things, you're transferring ingredients, you have stirring equipment that you're using. So throughout that process, maybe you lost some of that cookie batter on the spoon or on the mixer, or maybe some of it is still stuck to the bowl that you initially put all the ingredients in, right? So you lost a little bit along the way, and that means you're making less than you should. So you actually made 22 cookies, and you theoretically, if you followed the recipe, should have made 24 cookies. Obviously, you want to make as close to 24 cookies as possible, right? If you made all 24, just like the recipe says you should, that means you had 100% yield. Okay, a yield is how much you're making. The percent yield is the percentage of what you should have made. Okay, so the formula on the screen here is what you guys want to use when you look at percent yield problems. So how do you know if a percent yield problem is something you have to do? Well, the problem is going to have to say, determine the percent yield of blah, blah, blah. Okay? So write this down on your note sheet. What's the formula for percent yield? It is your actual yield. So this is if you actually did the experiment. If you actually did the experiment, you could measure how much you made, and that's going to go in your numerator. So here's a picture of a beaker with a precipitate in it. So you could figure out how much precipitate you should actually make. That's your theoretical yield. You could measure how much then you actually did get. Okay? Your theoretical yield goes in your denominator, and that is theoretically how much should you make. And that is predicted from your stoichiometry. This is really easy, guys. We know how to do everything for this process, all right, from what we've learned already throughout the unit. You have to understand, though, that your theoretical yield is what the math tells you, is what the stoichiometry tells you you should make. So in order to get a theoretical yield, you have to do a stoichiometry or a set of stoichiometry problems. You're going to get your actual yield from your experiment. So, most of the time we're not going to be doing the lab, right? But the problem will say you actually made or collected or produced. So you're looking for some key words here. So you're looking for words like collected, produced, okay, synonyms that go with those, all right, that you actually made, all right? And then that's going to go in your numerator. And then once you figure out your theoretical, what you should make, your theoretical value, you could easily find your percent yield and see how you did. So let's go through a practice problem, 2 of them actually, and then you should be good to go. So the first one is in your notes. It's the class example. Actually, the first 2 we're doing are the 2 class examples on the note sheet. It says determine the percent yield. So there we go. You know you're doing a percent yield problem because it asks you to. For the reaction between 28.1 grams of Sb4O6 and excess carbon, if 8.55 times 10 to the 22nd atoms of antimony, which is Sb, is recovered along with an unknown amount of carbon monoxide. So it sounds complicated, but it really isn't. What you want to do first is set up a balanced chemical reaction. So that's what we're going to put in the box here. So every stoichiometry problem has to start with a balanced chemical equation. So let's go ahead and do that. It says you are going to have a reaction between Sb4O6, let's write that in, and an excess amount of carbon. And it says you have 8.55 times 10 to the 22nd atoms of Sb is recovered. So recovered is a product. And an unknown amount of carbon monoxide. Those are your two products. So let's go ahead and balance this chemical equation. Okay, try to do that here real quick. I have 4 antimonies on the left. I need 4 on the right. I have 6 oxygens on the left. I need 6 on the right. And I need 6 carbons on the right. And I have 1 on the left, so I need to put a 6 there. And I guess a 1 there. So it looks like that's balanced to me. Okay, and I want to find percent yield. So I need to have my percent yield formula written out. I want my percent yield of antimony. Okay, how do I know that? It's because the problem says 8.55 times 10 to the 22nd atoms of antimony is recovered. Okay, so what's actually recovered here? The antimony is. So my percent yield of antimony is my theoretical yield of antimony on the bottom in my denominator, and my actual yield of antimony is in my numerator on the top. Okay, so this is easy to figure out if you could just read the problem. It's just reading comprehension. Figure out if the question says, asks you for a percent yield, figure out what data you have that is recovered or collected. Okay, and that's what we said here. Okay, collected, produced, recovered is another synonym for those. Okay, and that's going to be what you're solving for here. All right. So we want to find the theoretical yield of antimony. Remember, the theoretical yield from the previous slide has to be found through stoichiometry. Stoichiometry tells you what you theoretically should make. All right. So what are we going to solve for? Well, it says we have a reaction between 28.1 grams of Sb4O6. So remember how I told you to set these up. You want to have your data written underneath your chemical equation. Excess carbon, so I'm not going to write anything there really. And I have 8.55 times 10 to the 22nd atoms of antimony is recovered. So what I tend to do here is when I know what's actually recovered, I know what my actual yield is, I put a box around that, I label that actual yield. Okay? Here's the problem students run into here. They see a lot of numbers and they don't know what to do. Well, you want to isolate what's important, isolate where things go, and you'll be fine. So if you have an actual yield, you know that is going to go right here. Okay? That's the only time you're going to use that number at all. So I have students trying to use that number throughout the problem, and you don't want to do that. So if you have an actual yield, how much you recover, you're going to pop it right into your percent yield formula. So your percent yield of antimony is your actual over theoretical, and I'm going to pop in my actual right here. So this is really, really important. I'm going to put 8.55 times 10 to the 22nd atoms of antimony in my equation. So my unit is atoms of Sb. So in order to figure out what my percent yield is, I need to have consistent units, right? So if I have atoms of antimony on the top, I need atoms of antimony on the bottom. I'm not going to solve for grams or, I don't know, liters or some weird other unit because it's not going to match. So my theoretical yield has to be in atoms of antimony. So I'm going to set up my stoichiometry problem. The only thing I can start with is my 28.1 grams of Sb4O6. I'm going to go on my mole roadmap, my stoichiometry roadmap, and solve for atoms of antimony. Okay, so I can set this up by canceling out grams of Sb4O6 on the bottom, and you want to go to moles of substance A of Sb4O6 on the top. Then cancel out moles of Sb4O6 on the bottom and go to moles of substance B, in this case antimony, on top. And then cancel out moles of antimony on the bottom and then convert to atoms of antimony on the top. And figure out what your theoretical yield is going to be. Okay, so I'm going to have this pop up here on the slide for you. So you can pause the video if you want and write the numbers in. But we've done this before. This is just a basic stoichiometry problem here. Going from grams of A to atoms of B. Okay, molar mass of Sb4O6 is 583.04. 1 mole of Sb4O6 on the top. 1 mole of Sb4O6 on the bottom. of your next step, 4 moles of SB on the top. That comes from our coefficients from the balanced chemical equation. 1 mole of antimony on the bottom, 6.02 times 10 to the 23rd atoms of antimony on the top. You go ahead and solve that, and you end up with 1.16 times 10 to the 23rd atoms of antimony. Okay? So again, your actual yield, what I give you in the problem, 8.55 times 10 to the 22nd atoms of antimony, that determines what your theoretical yield is going to be, the unit on that, what that's going to be. So in this case, again, atoms of antimony is what we have. Let's pop it in. 1.16 times 10 to the 23rd. Make sure you use your calculator the right way. This should not be a big number, right? You have 8.55 times 10 to the 22nd over 1.16 times 10 to the 23rd. If you use your calculator wrong, you're going to get a really big number, and you shouldn't be doing that at this point in time. So divide the two, multiply by 100, and you end up with a percent yield of, it's okay, it's mediocre here, 73.3% for this experiment. Okay, obviously the goal here is a percent yield of 100%, which means you should have made, X amount of stuff, and you actually did make X amount of stuff. Most of the time it's not going to happen though. You should really never get a percent yield of over 100%. That means you should have made, you should have made 8.55 times 10 to the 22nd atoms of antimony, and you made more than that. Like, matter can't be created or destroyed along the way here, so you shouldn't be able to make more than what you calculated. Okay? So that's how you do percent yield problems. You have your actual from the problem itself, you find the theoretical from stoichiometry, pop them into your equation, and you're done. Let's go ahead and do this one. Okay? It's the next class example on your note sheet. You have 7.18 grams of hydrogen is reacted with 33.9 liters of nitrogen at STP to produce 36.9 grams of NH3. What's the percentage yield? So it's asking you for a percent yield, so we know we have to use our percent yield formula, which is percent yield of NH3 is equal to actual yield of NH3 over the theoretical yield of NH3 times 100. Okay? I know I'm going to find the percent yield of NH3 because in my problem, here's my keyword, I'm going to produce 36.9 grams of NH3. Okay? Once I find that value, okay, my actual yield, I label that actual yield, okay, and I save that to plug it into the equation right here. Okay, so I'm producing 36.9 grams. So I go into the lab, I do the experiment, I collect 36.9 grams of this NH3 product, and I know that's my actual yield. I'm saving it until then. I'm not using it anywhere else in this problem. So let's go ahead and write our chemical formula for what is going on, chemical reaction. I have hydrogen reacting with nitrogen. Oops. I'm already writing my product, so it's N2, yields NH3. Okay, I have more data here. I have 7.18 grams of hydrogen, and it looks like I have 33.9 liters of nitrogen at STP. So that's nice. There's no Pibnert stuff going on here because I'm at STP. I'm going to produce 36.9 grams of NH3. I want to figure out my theoretical yield of NH3. How much NH3 should I theoretically produce? So I don't know how many grams of NH3 I should theoretically make here. So what I need to do is convert 33.9 liters of nitrogen into grams of NH3 and 7.18 grams of H2 into grams of NH3. Why do I need to do two of these? Well, if you have two reactants, it's a limiting reagent problem, right? So I don't know here which one of these is my limiting reagent. I don't know how much product, NH3, I'm going to theoretically make here. So it's the same rules as before. If you have a limiting reagent problem, which means you're given two or more amounts of reactant, you need to make sure you do two stoichiometry problems. Okay, let's go ahead and knock these out, and we'll figure out what our theoretical yield is going to be. So we know how to do all this because it's just a theoretical, limiting reagent problem. So we'll start out with the hydrogen. We have 7.18 grams of H2. And I'm going to convert that into what here? Well, I have 36.9 grams of NH3 as my actual yield, so I need to figure out grams of NH3. So I'm going from grams of A to grams of B on my stoichiometry roadmap, which is a 3-step process. Okay, cancel out grams of H2 and go to moles of H2. Next step, cancel out moles of H2 to go to moles of substance B, which is moles of NH3. And the last step, cancel out moles of NH3 and go to grams of NH3. Okay, let's go ahead and plug some numbers in. I have grams of H2 in my denominator, so I need a molar mass. We've done this before. That is 2.016. So I have to take hydrogen times 2. 1 mole on top. Next step, I have to go back up to my chemical equation and realize I never balanced it. So I'm going to go ahead and balance that real quick. 2 in front of the NH3, 1 in front of the N2, and 3 in front of the H2. Okay, so I was over ambitious to start the problem. I forgot what to do here. So make sure you balance your equation first. That's what I should have done. So cancel out moles of H2. There's a coefficient of 3 in my chemical equation, so that goes there. And in front of NH3, there's a coefficient of 2. So I put that there. Last step, 1 goes next to moles. And I determine the molar mass of NH3. That is going to be 17.03 grams. So I go ahead, type it into my calculator, and I end up with a mass of 40.4 grams of NH3 produced from my 7.18 grams of hydrogen. I'm not done. I need to figure out what it would be with nitrogen. So let's go ahead and start out with that. I have 33.9 liters of N2. I want to, again, go to grams of NH3. So I'm going to go ahead and go from volume of gas of A into grams of B, which is, again, a 3-step process. All right, cancel out liters of N2 and go to moles. Next step, cancel out moles of N2 and go to moles of NH3. And the last step, cancel out moles of NH3 and go to grams of NH3. I'm at STP, that's really nice, so I know in 1 mole of nitrogen I have 22.4 liters of gas. Next step, coefficients from the balanced chemical equation. There's a 1 next to N2, and there's a 2 next to NH3, and the last step is the same, 17.03 grams of NH3 over 1 mole of NH3. Plug it into my calculator, I get a total mass, theoretical mass, of NH3 of 51.5. Okay, let's think about it. My limiting reagent problems, when I do these, I pick my smallest answer for how much I'm going to theoretically create. So I'm going to theoretically make 40.4 grams of NH3 in this experiment. That's how much I theoretically should make. If all goes according to plan, I have no loss of any reactants along the way, there's no sources of error, etc. So I kind of ignore the bottom equation here. There's the bottom stoichiometry problem. I know that my hydrogen, just to review, is my limiting reagent then, and I know my nitrogen is my excess. All right, I'll have extra nitrogen gas left over at the conclusion of this experiment. So I go ahead and I want to plug everything in. So I have my percent yield of NH3 formula. I'm going to have my actual yield of NH3, which I said from the problem is 36.9 grams. My theoretical yield is what I had on the previous slide. I said my theoretical yield will be 40.4 grams. Of NH3, multiplied by 100, and I get a percent yield here of pretty good. It is going to be 91.3%. Okay, 91.3% yield for this experiment, which is pretty good. It's not 100%. You're probably never going to get 100%, but it is pretty good nonetheless. If you're doing any of these practice problems and you get some low percent yields, that's okay. But if you're doing some of the practice problems and you're ending up with percent yields of over 100%, or on the test you do a percent yield problem, you're getting over 100%, you are doing something wrong. Okay, so I'm going to give you numbers and data that should give you realistic percent yields, and it's not realistic to really get over 100% yield unless there's some error involved. So if you do that, you're doing something wrong: calculator mistake, stoichiometry problem, error, or nomenclature error when you're balancing your equation, something like that. Okay, so there are a couple practice problems you guys are going to try. We'll do a couple more in class. This is the end of the unit, so it's all about practice, practice, practice right now, and doing as many problems as we can, get the hang of it, and you guys will be just fine. All right, if you need anything, let me know. Thanks, guys.